Hello everyone, welcome back on course of Higher Surveying, and today we are in the new module called Photogrammetry, which is module 6. This module has 8 lectures. First is the introduction, second one will be vertical photogrammetry, stereo photogrammetry, then we have analytical photogrammetry 1 and 2. Later we will cover photogrammetric products which are developed as a process of photogrammetry. Then we have 2 lectures on digital photogrammetry, which are very special lecture from the perspective of digital photogrammetry. Rather, they are the additional lectures, and one is image matching and other is close range photogrammetry. So, let us start with the introduction. So, these are the books. First 3 books are easily available in our country with low price edition. However, for remaining books which are listed here, you should go to some library, maybe public library or institute library, and I will say that you should refer these books there only, because little expensive they are. Okay, so let us start here. So first of all, if you look at the electromagnetic spectrum, that is the spectrum of light, this is the wavelength range here shown from right to left. Wavelength is increasing from right to left, so frequency increases from left to right. And you know the relationship, speed of the light is lambda into mu. Lambda is wavelength and mu is frequency of any electromagnetic wave. You might have come across some term called VIBGYOR, right? Violet to red colors. These are the 7 colors. So, this is violet and this is red. I can say that in the electromagnetic spectrum, the wavelength of the violet color is 400 nanometer and wavelength of the red color is 700 nanometer. And this is called the optical range or the visible range, because our eyes are sensitive to these wavelength range only. That means whatever color I am seeing here, this is the black color, this is the red and white color combination on the shirt, or this is the white color on this mobile phone. So, all these visible colors are in this range 400 to 700 nanometer. We have a term optical camera. That means the camera that works in the range 400 to 700 nanometer wavelength. That's called optical camera. Well, I hope that's clear now. Then let us start with the basic definition of photogrammetry. If I explain you in layman's language, photo means photograph that we acquire, and then you have metry as a suffix to this term photo, the photogrammetry. That means I want to do some kind of 3-dimensional measurement using photographs. So, it becomes photogrammetry. Similarly, we have terms like lidar grammetry, radar grammetry, right. So, these terms are using the same suffix metry, that means 3D measurement by some means. It could be photograph, it could be lidar, it could be radar, and so on. So, the standard definition of photogrammetry, which I have taken from some source, that is, photogrammetry is the art, science and technology of obtaining geometric information on the 3-dimensional shape and orientation of objects from photographs and other imaging sensors. So, what do you mean by photograph and image? Okay, so let us talk about the technical definition of photograph and image. So, let us say this is camera body shown here in the screen. Light enters into the camera, light goes to the film or sensor. What is the film? Film is polyester acetate based medium. Once it is sensitized or once it is exposed to the light, it cannot be used for second time. It is completely different from the digital sensor. So, light will sensitize the film. Once the film is sensitized, then we develop the negatives by some process, and from these negatives we develop positives, what we call photograph on paper, right? Or these positives are called the photograph. So, the idea here is, if you follow this process where light enters and sensitizes the film, and then from the film we develop negative and then positive, and so the output is called photograph. Let us consider another process where instead of film I have a digital sensor, right? So, the light will interact with the sensor, and this interaction release some photons, and those photons will generate some current, and this current will be generating some voltage, and that voltage we will measure and convert into some digital number like this. And my so-called product, that is what we call image, will consist of some digital numbers. The product is called image, and that is the difference between photograph and image. Now you can imagine we have something called photograph and image in optical region. However, for microwave region in the spectrum, we have radar, so we never have radar photos. We always have radar images. Why? Because there is no process like this in the radar. There is only this process available in radar, and that's why we say radar images. Similarly, we say LiDAR images, right? So that is the idea about image and photograph. As on date, we are using digital sensors, so that's why we should use the term image if you are using a digital sensor or digital camera. Let us start with the early stages of photogrammetry. So Kepler has first conceptualized the idea of camera. That means there is a person here, and if there is a pinhole in the box, so one can acquire this image. So image is looking inverted here, because a ray which is coming from this point, it is going to this point, and the ray from this point is going to this point, and as a result the inverted image is formed on this screen, and we call it negative or negative plane. There is another development by Nather. He first acquired the aerial photograph using hot air balloon. That means in the hot air balloon a person was carrying a camera, and he first acquired the aerial photograph. We should say aerial photograph because the camera was based on the film, not the digital sensors. Right. Later on, some more experiments were done. Cameras were mounted on the pigeon, and pigeon used to fly, and they used to bring the information. And the idea was to do spying, right? But still, it was not a bad idea to acquire the photographic information from a height. And that was the concept of doing the aerial photography. So in the early development, the first photograph that was developed by scientist Joseph Nisfone, and it took almost 8 hours. Well, this was the early stages of development. Then first practical photo was delivered by Jacques Maury, and then later on Dominique Francis used the term photogrammetry. That was his idea, conception. However, in reality, this term, the photogrammetry, was used by Dr. Albrecht. If we look into the history of photogrammetry, there are 4 stages. First stage we have already discussed, and that stage started from the 6th of the century. However, the real development started much later because of the resources, development and research and so on. The second stage was analog photogrammetry, where some kind of mechanical instruments were used to create the 3D from the photographs. Later on, photogrammeters shifted to analytical photogrammetry, and scanned photographs in the form of images, they are supplied to the computer, and by using the analog computers and the scanned images, we started doing the development, and that's why we call it analytical photogrammetry. Nowadays, with digital computers, photogrammeters started digital photogrammetry. So these are the basic 4 stages in the photogrammetric development. Today, we are in the era, or we are in the phase of digital photogrammetry. So concept of creating 3D model was there already. So by making the projection of 2 relatively oriented images using intersection of set of homologous bundle of rays. What's the idea here? If I have 2 images like this, if I place them parallelly, orient them appropriately, and if I take bundle of rays, means one ray from here, one ray from here, and they are targeting at some point on the ground. So using these 2 photographs or 2 rays, I can find out the coordinate or 3D coordinate of this point, and that started with the analog photogrammetry. So these are the basic inventions. If you look at planograph, double projector, stereo comparator, stereoautograph, autocartograph, stereotopographine, and all these are the early development in the analog photogrammetry. However, today they are obsolete after the invention of computers. The analog photogrammetry was replaced by the analytical photogrammetry. Further, the analog computers were superseded by the digital computers, and even the analytical photogrammetry was replaced by the digital photogrammetry. So, in case of analog photogrammetry also, this is the idea of vertical stereoscopy. So, I am putting two images together and trying to find out the 3D coordinate, and we will see all these concepts very carefully. In those days, they used to have machines like stereo plotters. They used to use this one to create the 3D using acquired photos from the aerial photographs. Okay, then if they were not able to acquire the photo by stereo logic, which means let us say there was some place on the land surface which could not be acquired with the help of stereo photographs, they used to follow the convergent photogrammetry. They used to put two cameras like this and two cameras not like this, rather on this view. They used to acquire the photo like this, and they used to develop the 3D models. The idea was to have some overlap between the two images. That means if there are two images, they are acquiring the same land, or they have some overlap more than 50%. So, with this overlap, they used to develop the 3D model for the only overlap area, not for the non-overlap area. Okay, the third phase was analytical photogrammetry. So, it was based on the stereoscopic vision of digitized images, which means photogrammeters started scanning out photographs, and images generated by the scanners were used as a soft copy images with the computers. So, the analytical photogrammetry started. If you look at the various developments, we have collinearity and coplanarity conditions, space resection, space intersection, interior and exterior orientation, relative and absolute orientation, we have bundle adjustment and self-calibrating bundle adjustment. So, these are the basic concepts. So, let us go one by one. Basically, we are trying to understand what is the meaning of these concepts. So, we will take only few which are very important to understand now, and we are going to deal in detail with these concepts in coming lectures. Let us say this is terrain and there is a point, we call it the object point. Okay. There is an image and a positive. So, this is my negative image or film plane, or I call today sensor. Well, this is my positive plane here. That means positive that I developed up from the negative. So, this is camera assembly where there is only negative is there. Let us see that this point has been imaged on the negative, and this is exposure station through which light passes into the camera, or light goes into the camera, okay, and then it creates, this is image of the point. So, this is image of the object point. We call this point as image and not this point as image. Remember, this is the impression of object point on the negative film. From the negative film, we develop the positive, and on the positive wherever this point comes, we call image of the object point. And there is a reason for that. Let us say there is another point on this terrain, and there is a point here called B point, and this is A point. Okay. So, if I try to make an image of the B point, it will create some impression here. This is small b, this is small a, or let us call A dash and B dash, and let us call this point as small a and this point as small b. We have some kind of experience of looking at the terrain. The idea here is, suppose if I am standing here, then I will see the point B is on my left hand side and point A is on my right hand side. But if I look at the negative, I can see here that A dash and B dash are relatively inverted. That means now from my position here, point A dash on the negative is on the left hand side, which is completely contrary to the position of point A in the field. Similarly, you can see that B is imaged at B dash, which is on the opposite side with respect to this axis here, right. However, if you look at the positive, they are on the same sides, and I have the same experience. The way I am looking at the world, I will get the same experience in the positive, and as a result, we always use positive for referring the any point on the image. So, we use the positive image, not the negative image. If you look at the sensor, they first create the negative and then internal software shows the positive on the screen, right. So, you should understand it. So, although you are looking at the same thing in the camera, what you are looking at the world, but that is developed by the camera. So that has some internal software to do that. If I look at point A, so small a here and this exposure station, they are all in one line like this. They are falling in a straight line, one three-dimensional line. And this relationship is called the collinearity relation. That means object point, the image point and the exposure station, they are in one line, they are collinear, and that is why it is called the collinearity relationship. I hope it is very clear and very easy to understand. Let us look into another one, the coplanarity. What is the coplanarity? Let us look into that. So let us see, there is a object point here, there are two images and both images are acquiring scene or information on the ground, and let us say object point is acquired in both of the images like this. So I can call it point A. So let me call this A left, this is A right. Now if I orient carefully these two images such that point A, this exposure station and this exposure station, they may come in one plane. So these are image points. I have drawn this plane. So if this plane will contain the exposure station O left, O right, image points A left, A right, and the object point. So these points O L, O R, A left, A right, and object point A will be in one plane. And this relationship is called coplanarity. They will be in one plane, coplanar. So it's called coplanarity relationship. Now let us divert to the types of photogrammetry. So now we are talking about digital photogrammetry after the analytical photogrammetry. In digital photogrammetry, only sensor has changed. That means earlier we used to have film-based cameras. Now we have digital computer and digital sensor, which is my digital camera. And we have two technologies, charge coupled device CCD and complementary material oxide semiconductor CMOS. In most of the cameras we use today, CMOS is more popular because it is less expensive. In case of digital photogrammetry, because of the use of digital computer as well as digital sensor, there are some distinct advantages, and these advantages brought new developments compared to the analytical photogrammetry. Okay, so first of all we have fully automated processing of the data, and as a result there are very important things, for example image and feature matching. Suppose there are two images and they are having some overlap or they are having information about the same area on ground. So we say that they are overlapping images. So now I want to find out which point here is also there. That means which are the common points in two images. So that's why we say image and feature matching. Then we have automatic type point generation. Let us try to remember right now, and we will talk about these in detail in coming lectures. Then we have important development like scale invariant feature transform, SIFT algorithm, and this is very important in the era of digital photogrammetry. After the discussion on the various phases of the photogrammetry, so let us talk about the cameras. So we have in general two types of cameras, as we already disclosed it to you few minutes back: film-based cameras and digital cameras. Yes, in case of film-based camera, we have a negative film which can be exposed only once to the light. It is placed in the camera, the cover of the camera is closed, and then the moment I take the photograph, light enters into the camera, it exposes the film, and that film cannot be used anymore. It has to be shifted and the new piece of film has to be replaced. Okay, so once we do, we again repeat the same process and again we shift the exposed film. There are 36 pieces of the film connected together in one reel. So once the reel is over, camera indicates you, this means all the negatives are exposed. So then you will replace the whole reel by another reel, and then you keep on acquiring the photographs like that. That means you keep on exposing the films. It was slightly expensive affair because I cannot reuse the used film. Okay, the film which is already exposed now has to be brought to the laboratory. There by some chemical process we used to develop the films, and after development we used to call them negatives. From those negatives which are permanent in nature, now we used to develop the positives. So what do you mean by permanent in nature? When film is exposed in the camera, at that time I cannot use it. So we need to brought into the dark room where there is no light available. In the dark room, there is a standard chemical process through which film passes and it becomes a permanent. So that means features are acquired in the film, they will become permanent on this. Using those negative films, we used to develop the positives or photographs in the hard copy. So this was the process of film based cameras. In case of digital camera, we click it and then we immediately transfer our data to the laptop or computer. So that is a fundamental difference in the analog camera and digital camera. This categorization also true for aerial cameras and satellite cameras. Satellite cameras nowadays are completely digital in nature, but at times in around 1950 to 1975, they were in the analog mode also. That means we used to have film based cameras in satellite also. And famous Corona satellite program was having a panoramic camera. You can read the details on internet about that. Let's talk about the consumer grade camera, which means being a consumer, I am using some camera. It could be SLR camera, it could be point and shoot camera, it could be mobile camera, all are consumer grade camera. We have a consumer grade camera, film based as well as digital. Most of you and including me today, we are using digital cameras. There are some passionate photographers, they still use film based camera today because they have a passion to use those. Rather, they are habitual of using those and they feel there are a lot of advantages with analog camera or film based camera. No problem. But nowadays, most of us have already shifted to digital cameras. In case of digital camera, once you take the photograph which is acquired by the sensor is transferred to memory, and that's the reason it vanishes the information, whatever it acquires, and it is again ready to acquire new information. And that is the advantage of the digital camera. And hence, this technology has more or less replaced the film-based technology. Okay. So now we have small format, medium format and large format. And these formats are also equally applicable to aerial cameras. In the digital camera, there are frame cameras. So what do you mean by frame camera? The moment I click it with this camera, what happens? In one click, it acquires some information on the frame, what we call frame. And it exposes the whole frame of the sensor or maybe a negative film. And such kind of cameras are called frame camera. So we have digital frame camera as well as earlier we used to have frame camera which were film based cameras. Then we have stereo camera. What does it mean? They have two cameras into one box and using stereo principle, they are acquiring the 3D model directly. Well, we will look into that, but we are just talking about the digital cameras available in the consumer grade range. Now, let us talk about the platforms. Platform means something that carries the camera so that camera can acquire the information on the ground surface. So, the first is satellite. Okay. In case of satellite, satellites are projected by the rockets in their respective orbits. They also carry the camera which is already mounted and the camera acquires the information. For example, Landsat, even the Corona satellite was having some panoramic camera mounted on that. Then we have QuickBird, Spot, Iconos and many such sensors are there. Similarly, we have shuttles, they can also carry the camera in the space. Now, on terrestrial and airborne platforms, we can also mount the camera. If we see that there is a tripod with a reamed bar, that means on this reamed bar here you can see camera is mounted and this gentleman is trying to acquire image or information. Similarly, there is a tripod here shown in this figure in the image where a camera is mounted over the tripod. Still cameras or the photographic camera, they also are mounted on the tripod to acquire the image information. What about the helicopters and aircrafts? Helicopters, sometimes you will find out a term called rotary wing is used. For aircraft, you will find out some term called fixed wing aerial vehicle. This term is used, so I am writing this also. Yes, helicopter as well as aircraft both can also carry the camera for aerial photography. So now we have a terminology. If I use the camera on platform which is on the ground surface, it is called terrestrial platform. Similarly, if I mount the camera in the aircraft or helicopter and they go up to certain height, which is quite a high, then we call it aerial platforms. So, helicopter and aircraft are aerial platform, while tripod and let us say tripod with a reamed bar, they are terrestrial platforms, right. What if you carry yourself a camera and try to do the photography without tripod? Well, it will be called terrestrial photogrammetry, because you yourself is acquiring the photo on the surface of ground and you are carrying yourself and your height is more or less very limited on the surface. Recently, there is some more development happened in platforms. So, recently scientists and well as practitioners of the photogrammetry have introduced a new term, low altitude platforms. That means they are not terrestrial platforms like tripod, they are also not aerial platform like helicopter or aircraft, they are in between the two. First is the pole. Pole means 30 feet high pole, and the top of the pole we make some arrangement to hang a camera, and by some automatic arrangement on the ground we try to control it and camera acquires the images from that height of 30 feet or maybe 20 feet. So, that is the arrangement to call pole, and that is low altitude platform. Well, then second is kite. It has some special material that we fly in the flow of air, and that thread which is connecting the human and the kite, it has some arrangement to suspend a camera in the air. When kite reaches to its peak height, at that time camera acquire the information. Similarly, we have a blimp. Blimp has helium gas filled into that, or even we have balloon. Blimp and balloon are the same kind of arrangement where they have helium gas, which is quite a light gas, and then that balloon is again the carrying the camera on its thread, and thread is connecting the human and the balloon. Suspension arrangement is also there, and using that suspension arrangement, camera is suspended in the air, and at certain height we try to acquire some information using the automatic triggering mechanism. So, that is the idea here. Further, we have drone which can go to 150 meter, 200 meter heights. So, they are also low altitude platforms. Remember, the drone carries the camera. Drone is a platform. Here you can see there is a DJI Inspire platform and this is a camera here. Let us talk about the type of aerial photographs. Based on the position of the sensor, we have vertical photographs, tilted photographs and oblique photographs. That is a field of view of the vertical photograph. What is the meaning here? If I draw the optical axis of the camera, which is completely matching with the nadir direction or the gravity direction here like this. So, if the optical axis or the camera axis of a camera, it is in the direction of gravity, then we call the photograph acquired this vertical photograph. It is very simple definition to understand. We will again try to modify it in the coming lectures, where we find out there are more criteria to define a vertical photograph, and this is the coverage of the vertical photograph from here to here. Okay, what next? Then we have tilted photograph. That means this is the gravity direction, but the axis of camera is somehow tilted, and as a result we have this as camera optical axis, and the photograph acquired is called the tilted photograph. That means we are acquiring a tilted photograph. Naturally, we should expect some distortions in the tilted photograph. What are the distortions? Distortions is something away from the expected one. So, vertical photograph covers this area, but tilted photograph, instead of covering this area, it will cover some kind of shifted area. If I further tilt the axis like this, then the photograph acquired is called oblique photograph. You will be surprised to see here that there is a limit. If the axis is within 3 degrees, it is called tilted photograph. Vertical photograph, there is no deviation of camera axis from the gravity direction, that is called vertical photograph. That means there could be some random error, but knowingly we do not commit any error there. But in case of tilted photograph, the deviation is there up to 3 degrees. More than 3 degrees, it is called oblique photograph. That means the deviation of camera axis from the gravity direction is more than 3 degrees, it is oblique photograph. If it is Up to 3 degrees, it is called tilted photograph. If it is 0 degree, it is called vertical photograph. Okay, what about the angle of coverage or field of view? In the last photograph, I have shown you two lines like this here, this point and this point, that is coverage of the photograph. This much length a camera is going to cover on ground surface. And this is image plane, or what we call negative plane, or we can call it negative image plane. This is exposure station here, this cross. So this is focal length from here to here, f, and then this is called field of view of camera, and it is, this camera is going to acquire this much of length, or I can say in 2 dimensions this much of area. If I consider the 2 dimension of the camera, then let us say this is length that is being acquired by the camera. So this angle is called FOV, which is alpha 1 here, right. Now if I increase the FOV, it becomes, let us say, alpha 2, which is more than alpha 1. You will see here, for the same arrangement of camera, as we increase the field of view alpha, focal length will has to be reduced, and that is also true for the consumer grade camera or terrestrial camera. Similarly, if I further increase alpha, that is field of view, focal length has further reduced. So if I have higher coverage, I will cover more length on the ground, but at the same time you can see that focal length will reduce. And we will see in the next lecture, if focal length is less, I will have less resolution of the image. We will talk about this thing, but for time being you can just collect this information. Similarly, focal length is higher here, so I will have less area to cover compared to this area, so I will have higher resolution. Suppose you have a 20 megapixel camera and you acquire some area, and now if you divide that length or area into 20 megapixels, so each pixel will have certain value on the ground surface or on the wall, and that is called the resolution. So we can see that the resolution is somehow represented by the pixel, although it is not very correct definition. For right now you can assume it to be correct, we will modify it later. So as you see that if you have wide angle camera, you will acquire with the same 12 megapixel more coverage or more length on the ground surface or on the object surface, or each pixel of the 12 megapixels will represent higher length of the ground, or I can say less information compared to the earlier arrangement what we talked. So that's the kind of idea why we have higher focal length if coverage is less, and as a result we will get higher resolution. If the FOV is between this range, it's called narrow angle photograph. Then we have this range for normal or standard angle photograph. Then we have more than 90 degree to 1110 degrees, we have wide angle photographs, and more than 1110 degree FOV is called super wide angle photograph. Or rather I should say, is it camera or is it photograph? No, because camera can have varying focal length, and as a result field of view can also vary. And so we say that whatever arrangement I make at that time of acquiring the photograph, it will characterize photograph, not the camera, because camera has a lot of facility, right. So we do not attach these values to the camera, rather we attach these values of FOV with the photograph. Let us look into the basic terminology of the camera. There is object which is imaged here, so there is a lens assembly here, and then it is imaged invertedly here. Rays are converging from this point and rays are converging here. So this distance from the center of lens to this distance is called focal length, and from this point if I go towards object, this is called distance O here, and if I go towards the image from this point, it is called I, and then I can write this famous lens equation like this. So now it is shown here that all these rays, they are basically converging on this point, let us say A, and all these rays, they are basically converging at point B here, let us say small a, small b. So that is the idea here. So we are showing only one ray here, here multiple rays we are showing. Now coming to the aperture, if you look at the camera carefully, then should be a hole that allows the light to get into the camera system, and that hole is called aperture. Larger the aperture, more light will go into the camera and it will create bright images. If the aperture is completely closed, no light will go. If aperture is open slightly, minimum light will go, and so it controls the image quality, illumination on the image. So basically the function of aperture is to control the amount of light to the camera. As we know that we can vary the focal length, similarly we can vary the size of the aperture. So what is the effect here? There is a focal length like this. This is the object here on the right hand side, and there image has created of this object. Now let us think that you have increased the focal length from here to here by bringing lens towards the object. That means if you open your lens telescopic tube, it will more in the length, and as a result you are increasing the focal length, and because of that what will happen? The size on the image will be increased here. But you can see here the amount of light that was coming earlier is still same because aperture is same, the opening is same, and as a result you will get dull image or little less illuminated image compared to this image, right? On the other hand, what if I want to have the same illumination, but at the same time I want to increase the focal length? That means I want to have higher details. I need to increase both focal length as well as aperture size. Okay, that we are showing here, and now we are getting larger image or image with higher details, as well as we are getting same illumination what you get here in this case. So now we understood that there is some relationship between the focal length and aperture size, and aperture is controlling the amount of light or the illumination, and focal length is controlling spatial quality, the details, right? So let us have the relationship between the two. So aperture diameter and focal length ratio is called relative aperture. The ratio of focal length to relative aperture is called the f number or aperture stop, and it decides the brightness of the image. Secondly, the ratio is independent of the focal length. It is indicated by f by n, where n is the f number. Okay, what is the meaning here? Let us say I have aperture area A, and if I reduce it by 2, that means I am reducing the amount of light by 2, or I can reduce it by 4 times, 8 times, and so on. What will happen? I need to reduce the diameter of the aperture by under root of this, let us say under root of 1, under root of 2, under root of 4, and so on. So accordingly, diameter is reduced by root 2, root 4, root 8, and so on. So you will find out these are the f numbers, f1.4, f2, f2.8, and so on. So they are representing the diameter of the aperture, not the area. If you make it a square of this, 1.4 square, it is 2. 2 square, it is 4. So it is indicating that we are reducing the area by a factor of 2. So let us see, this is lens. So rays are going like this, focusing here, right? So aperture size is highest. Now aperture size I am reducing. So here, and then here again I am reducing the aperture size. So basically this arrangement is going on like this, and generally we have in this ratio only f1.4, f2, f2.8, and f. They are fixed discrete values available with the cameras. Okay, so what is a shutter? It controls the timing of opening. So aperture is opening, and if I control the shutter, that means I allow the light for certain duration, and that is called operation of shutter. So shutter is kind of shutter of the shop. So you open the shutter, light will come, and if you close the shutter, light will not come. If you open it, shut it, it will come for that duration. So that is the operation of shutter. Now shutter speed, imagine that you have a pet dog, he is making some natural movements, or you want to capture it. If it runs very fast, and if you use a camera, you come across some blurred images, because if the shutter is opened for large time, during that time that movement has happened, and as a result you get blurred image. What is the solution here? Open the shutter for very less time. So during that time, even that movement happens, it is so less movement that it will appear as a static object. So that is the operation of the shutter. So you can see here different shutter speeds. So if we have high time for exposure compared to this time, I have very clear image because the shutter speed is 1 upon 500 second. That much of time if we open the shutter and close it, and I get very crisp image. Now focal length, there is a lens assembly and it is called front nodal point N1 and there is a real nodal point N2. So the distance between the real nodal point and the image plane, it is called the focal length. In the digital camera, we have equivalent focal length concept. Let us say this is camera and this is the lens here. So this is the focal length because image is placed here. This is sensor, a film sensor. Now rays are coming from infinity, so they are parallel. They will be imaged like that with the help of lens. Okay. So this is called full frame sensor, which has complete size like this. Our mobile cameras have a sensor. We reduce the size of the sensor and that is called the cropped sensor. Okay. Let us make the camera small. Okay. And this is lens. Fine. I have reduced the size of lens also because I want to bring miniature cameras, small cameras. So light is entering like that. It is being focused like this. So the size of the sensor has also reduced now, you see, compared to the earlier sensor. So this is called the cropped sensor, and as a result of that, now you can see we have small cameras, and cameras are so small that we are fitting into our mobile phones, and that's the reason they are all cropped sensors. So this is cropped sensor compared to the full frame sensor, right? Full frame sensor is 35 mm full frame sensor, and the definition of full frame is 35 mm or sometimes 36 mm into 24 mm. Now ISO number. ISO number is controlling the quality or the radiometric quality or the brightness of the images. So camera provides higher ISO number. Even in the time of dark, it can acquire good images. So it is the sensitivity of the camera to the brightness of the scene. Now resolving power. Okay, what is the resolving power? In general, we can say if there are two objects like this, side by side, let us say one is my hand, one is my mobile camera, and if I take the photograph, in the photograph, if these two objects are appearing distinct objects or two objects, I will say that the camera is able to resolve the distance between the object and this object. So this is the distance here, right? So let us say this is the distance shown by my finger between the two. So this is the distance here. This distance is resolved by the camera. Now we have three terms here. The well resolved, that means I can see two objects as a distinct objects. Just resolved, that means they are appearing very close to each other, but still they are distinct. And finally not resolved, they are appearing as. Now we have just talked about the resolving power of lens or the resolution of camera. Okay. So let us look into the relationship between the resolution, field of view and focal length. If I increase the focal length, resolution improves, and you can understand it by simple logic. I have 12 megapixel camera, so 12 megapixels are acquiring this much of space. Let us see this tablet, for example. I increase the focal length, I can see that the less space on this tablet will be acquired. Again, so number of pixels are fixed, and as a result, each pixel is acquiring less space. And if there are small objects, I can distinguish them very easily if pixel size on the ground is small. If I have high resolution, that means pixel size is small. Similarly, higher the focal length, higher the resolution, higher the focal length, less the field of view. So automatically field of view is inversely proportional to the resolution or focal length. We talked about the cropped sensor. Now we have crop factor. If I take the standard film camera of 35 mm film, and if I calculate the area, that will be equal to, if I take the ratio of this divided by the cropped sensor area, the area of full frame divided by the area of crop sensor, it is called crop factor. What is the FOV of the crop sensor? It is FOV of the full frame divided by crop factor, direct relationship. What about the focal length of crop sensor? focal length of the full frame divided by under root of crop factor. So, you will get the focal length also of the crop sensor. That means, you find out what is the focal length of this Apple iPhone 5, it should be around 4 mm. Try it yourself, use the crop factor logic. We have learned all the things about camera, platforms and other terminology. What photogrammatists say ultimately about the camera? They say three things. Camera is non-metric camera, camera is semi-metric camera, or camera is metric camera. Non-metric means the interior orientation parameters are not known. All the consumer grade camera are non-metric camera. So, there are three interior orientation parameter. Focal length is one of them. So, if focal length is not known or the three interior parameters are not known, then it is called non-metric camera from the photogrammetry perspective. If out of three parameters, let us say focal length is known, we will call it semi-metric camera, or even the other two parameters are known and focal length is not known, we will say semi-metric camera. And if all the three parameters of interior orientation are known, we will call it the metric camera. So, that is the definition from the photogrammetric perspective. For the photogrammetry, for the 3D measurement, focal length plays a very vital role and we should know its exact value. And that is why we go for the calibration process, where we determine the calibrated focal length and the location of the principal point. These are three parameters of interior orientation of camera. So, a metric camera always know these three parameters. Right. So, in the next lecture we will start with the vertical photogrammetry, and there whatever we discussed today in this lecture, they are the preliminary knowledge about the photogrammetry field, but they are important information without which we cannot proceed further, and that is why this lecture is designed like that only. So, let us meet in the next lecture on vertical photogrammetry. Thank you.